Okay, so we've reached that part of the course where we're going to be doing some experimental measurements quite soon. So I thought it'd be good to get straight some basic facts about handling experimental data. And one of these is when you make a series of measurements and you want to know whether to accept or reject a particular data point. Is there an objective way of deciding on this? And the answer is yes, there is. So we'll be describing that. And secondly, when you're combining measurements together, say, for example, you're making a measurement of density, which is mass per unit volume, and the mass has an error in it, and the volume has an error in it. How do you combine those two errors together to find out what the error in the density is? Do you take some sort of average of the two errors, or is there a more objective way of doing this? And yes, there is. So we'll be dealing with that. But first of all, I thought it'd be important just to get straight that you understand the difference between accuracy and precision, because they're not the same thing. And just to give you an example, imagine you're taking a penalty kick in a football game, association football game, and you take the kick and you don't score a goal, but you hit the post. And then you take the kick again and you hit the post again in the same place. And you repeat this time and time again, and you keep on hitting the post in the same place. Well, what you're doing is being very precise, because you're hitting the same place every time, but not accurate because you are missing the target. So a measurement can be very precise, but not accurate. And this is usually due to what we call systematic errors. Right, so that's accuracy and precision. They're not the same thing. A value can be precise, but not accurate, which is how close to the true value a measurement is. Now consider the case where you make a series of measurements and you want to know whether to accept a particular data point, which looks a little bit out, but you're not sure, or whether to reject it. Is there an objective criteria for accepting or rejecting a data point or data points? And yes, there is. And it's all based on, well, the simplest way is based on standard deviations. All right, let's just see if we can advance the screen. There we go. Okay, so for this we need to consider means, the formula for standard deviations, and I'm sure for many of you you'll be familiar with these, but there's no harm in doing a bit of revision. So first of all, the mean of n measurements. The mean, represented here by x with a bar up across over the top, is the sum of the measurements divided by the total number of measurements. So x bar is a sum, this symbol sigma here, xi divided by n. So you calculate the mean, x bar, and then to calculate the standard deviation, SD, what this is for each individual measurement, you subtract the value of the mean, and then you square that value, and then you add all these squared values together. This is the summation term here. Then divide by the number of measurements minus 1, and take the square root of that. That is the standard deviation. So you determine the difference between each data point and the mean. You square the differences. You sum the squares, divide by the sample number, sample size, n minus 1, and take the square root of all that. And then you can calculate a standard error, SE, which is the standard deviation divided by the square root of n. The standard deviation and standard error are not the same. That's important to remember that. But now we've defined the standard deviation, how to measure it, we can then define a criteria, a simple criteria for rejecting a data point. Okay, this is not a full error analysis course. What I'm doing here is giving you a simple criteria, the 2 standard deviation criteria for rejecting or accepting a data point. And that is, if a data point lies more than plus or minus 2 standard deviations away from the mean, then it can be rejected. And a new mean and standard deviation and standard error can be calculated. So we're going to illustrate that with an example. Okay, let's consider this. We made a series of measurements on the number average molecular weight, MN. It's the same as molar mass, but it's molecular weight because we measured this in daltons or kilodaltons. And these are made from an osmotic pressure experiment on a solution of ovalbumin, our favorite protein. It's actually a glycoprotein because it's glycosylated in or under controlled solvent conditions, pH 6.8 and ionic strength I of 0.1 molar and 20 degrees centigrade. Okay, we're making measurements on the number average molecular weight using osmotic pressure. We made 8 measurements, and these are the values we get: 44.3 kilodaltons, 43.8 kilodaltons, 44.5 kilodaltons, 43.7 kilodaltons, 40.5 kilodaltons, a little bit lower, so that might be out, 44.2 kilodaltons, 43.9 kilodaltons, and 44.2 kilodaltons. Okay, so we now calculate the mean, standard deviation, and standard error. And then from that, we're going to decide whether the points, or any points, should be rejected based on this 2 standard deviation criteria. Right, so first of all, you have to work out the mean. So the mean, x with the bar over the top, is the sum of the values divided by the total number of values. So it's this number divided by 8, and we get a value for the mean of 43.6 kilodaltons. Then we calculate the standard deviation. And for that, we need to take each value. From each value, we subtract away the mean value and then take the square of that difference. So for this, we end up with 0.7 squared. For this, 0.2 squared, 0.9 squared, 0.1 squared. And this one gives minus 3.1 squared. Of course, the minus squared becomes a positive. And then 0.6 squared plus 0.3 squared plus 0.6 squared divided by 7. And then we take the square root of all that. And if we do that, we end up with a value of 1.3 kilodaltons. Then we can calculate a standard error, which is a standard deviation divided by the square root of 8 in this case. And that gives a value of 0.5 kilodaltons. And of course, we now have the SD, standard deviation. We can apply this plus or minus 2 standard deviation criterion. So 2 times 1.3 is 2.6. So we look for points which are plus or minus 2.6 kilodaltons away from the mean value. And in fact, if you look across the data, there's only one which falls outside the plus or minus 2.6, and that's this point here. So we reject the 40.5 kilodaltons point. And if we do that, we can calculate a new mean, this time with only 7 values, of 44.1 kilodaltons, a little bit higher. The new standard deviation is 0.6 kilodaltons, a bit lower. And the new standard error is 0.2 kilodaltons again, which is lower. So the final value for our number average molecular weight is 44.1 plus or minus 0.2 kilodaltons. Now, as the original data is given in terms of 3 significant figures, then we stick to that in describing the final answer, 44.1 plus or minus 0.2. And the number of decimal places in the error is the same as, is always given the same as those in the main number. And note how we've enclosed this in brackets here, because the number and the error both have units of kilodaltons. So that's how to cope with a set of data and to apply an objective criteria to accept or reject data points. In fact, we've accepted 7 and rejected just one of the data points and recalculated the mean and the standard deviation and standard error here. Okay. The next thing is when we combine errors together, and there are various situations here. Let's, for example, we want to know calculate the error in the mass of, let's say, an apple and a banana. We weighed the error of the apple, we weighed the mass of the apple and the banana. It comes with error. What is the error or total error of the apple and banana together? So if that represents the error in the apple, and that's the banana, you simply square the errors, and the square of the error of the banana and apple together is simply the sum of the squares of the errors of the apple and the banana. And then to get the error, you simply take the square root of that. So that's the simplest case. There are other cases here where the quantities are multiplied or divided. There we're dealing with relative errors. And then there were cases here where we're dealing with more than 2 parameters, 2 combinations of parameters. And when we've got constant terms such as lambda and mu here, then the formulae are generally different. Although in the case of this, so long as there's no error in the constant, then the constant value has no bearing on the total error of this summation or subtraction case. But the constants do affect the cases where they are multiplied or divided. And this is a set of cases here, the simple case here, and more complicated cases here, which you don't need to remember, like these, but know how to use them. So you can refer to these formulae and make the calculations. This is constant multiplying the parameter, a constant, and then the parameter dividing into it. And this is a case of a power, and then exponential, and then log, not natural logarithm here. And these are the formulae for calculating the errors and some simplifications here. So let's consider an example. Just considered a protein, ovalbumin, which is our favorite protein, or glycoprotein. Now let's consider a virus, a plant virus, a spherical virus. It's our favorite as well. Tomato bushy stunt virus. And we measure this radius from dynamic light scattering, and we want to know what the volume is. And thus, this harks back to my days when I was a postdoc research fellow, when I was researching, part of my research is on plant viruses, these wonderful spherical plant viruses. There's another plant virus called turnip yellow mosaic virus. It's also spherical. But this was rather nice for testing out concentration dependence theories because it didn't aggregate. So almost like a nature's perfect sphere, which remained as uniparticles, did not aggregate. Anyway, this is the case for tomato bushy stunt virus. You're given the radius, and you have to calculate the volume. Because you're given an error with the radius, then the question is expecting you to calculate the error in the volume, and it's given the radius in nanometers and also in centimeters. So what's the volume V in centimeter cubed? Well, the volume is simply 4/3 pi r cubed. So the first part is working out what the volume is, and it's 4/3 pi r is r cubed 1.5 cubed, and then 10 to the minus 6 cubed is 10 to the minus 18. So the volume is 14.1 times 10 to the minus 18, or in standard form, 1.41 times 10 to the minus 17 centimeter cubed. Now, how do we calculate the error? So we look in that set of cases and look for one that matches our case, where we have constant multiplied by the parameter to the power of 3. So which in that set of formula we've just been looking at matches that? Well, in fact, it's this one here. So A would be the volume, B is the radius, lambda is 4/3 times pi, the constant, and mu is another constant. In this case, it's the power of 3. So this would be the formula which corresponds to the volume calculation. And this is the error described here, and it's a simplification of that equation over here. So to work out let's just move that formula across. So this is the appropriate formula, where A is the volume, lambda is the constant term, which is 4/3 times pi, B is the radius, and mu is the power, which is 3. So that's the appropriate formula for the volume. And if we move across the relevant error term, so the error in the volume, delta A or delta V, is mu, which is 3 times the volume, 1.41 10 to the minus 17 divided by the radius b, which is 1.5 10 to the minus 6, and it's the modulus of that. So whether it's positive or negative, it's positive. Minus makes it positive. It's positive anyway. Times the error in the radius, which is 0.1 10 to the minus 6 centimeter cubed. And if we do that, we get a value for the error, total error in the volume of 0.28 times 10 to the minus 17 centimeter cubed. And so the volume is 1.41 plus or minus 0.28 times 10 to the minus 17 centimeter cubed. Now we could round that off to 1.4 plus minus 0.3, but since the original data is given as 3 significant figures, it's more appropriate if we leave the answer as in 3 sig figs. So the volume is 1.41 plus or minus 0.28 10 to the minus 17 centimeter cubed. And we've used brackets here, which presents the answer in an elegant sort of way, since both that number and that number are multiplied by 10 to the minus 17, have unit centimeter cubed, and the numbers of decimal points in the error is equal to the numbers of decimal points in the value itself. So that's how we can calculate the error of a measurement, which depends on more than one other measurement. In this case, it's the radius, which has been cubed. So that's it. That's some basic facts about handling experimental data. We've covered the case of accuracy and precision, showing that they're not the same. A value, a measurement can be very precise, but not accurate. We've dealt with the case of whether to accept or reject a data point from a series of measurements based on the relatively simple plus or minus 2 standard deviation criteria. We've dealt with the case of combining errors together in an objective way. We've given you a set of formulae depending on the particular case that you're dealing with. You don't have to remember those formulae, just to be aware that they exist and know where to look when you're making a calculation which involves the combination of error. And finally, in terms of a book about this, then I can strongly recommend this book here, Handling Experimental Data by Pence and Schott. It's published by the Open University, and I used to work for the Open University part-time as a tutor many years ago, so I had access to this sort of material, and I know how good it is. Okay, thank you.